Hi there, this is Mrs. Larson, and we are going to look over what linear functions are. So, we've been dealing this with before. We've seen linear equations. The only big difference is that we have the word function. So, the linear function equation looks like this. We've got an f, we have parentheses with x, and we're going to set that equal to mx plus b. Now, we've seen this part before, and the only big difference is that y has been replaced with f of x. This is like fancy y, and we call this f of x. We can replace f with any letter that we want. This is just what we would call the function. We're naming it f of x. We can call it g of x, b of x, whatever we want of x. Now what this says is that this is the value of the function when we plug in a value for x. So we're going to evaluate this function f of x is equal to 3x plus 5. We're going to evaluate when x is equal to negative 2 and 4. So we're just going to plug in these values one at a time. So how to do this, you take f of negative 2, which is now x, and plug it in anytime you see x into the function. So 3 times negative 2 plus 5, and we're going to go ahead and use the order of operations. We get negative 6 plus 5, which is negative 1. Do it again. We're going to try it with f of 4. So at f of 4, we plug in 4 for x. So 3 times 4 plus 5 is equal to 12 plus 5, which is 17. So what this means is that f of negative 2 is equal to negative 1. F of 4 is equal to 17. Now this notation allows us to evaluate when x is whatever we want it to be. And it's just like we've done before, but it's just a new notation. What I'd like you to do is go ahead and try the u-try. I'd like you to evaluate this function when x is negative 1 and 5. The function that you have is f of x is equal to 4x minus 2. Go ahead and push pause, give it a go, and then when you're ready, push play and you will be able to see the answer. Alright, so if you did this correct, this should be your setup. And so what we end up getting is at f of negative 1, we got negative 6. For the function at f of 5, we end up getting 18. So, we've done this before. It's now in this new notation. What we're going to do now is we're going to turn things around. I want to know what the value of x will be so that the function has the given value. So I'm going to give you the function g of x is equal to 5x plus 4. This semicolon is telling you that after this, I'm giving you that the function is equal to 19. This means that 19 is equal to g of x. So we are going to substitute 19 for g of x, and it looks like this. 19 is equal to 5x plus 4. Now from here, I want to know who x is. So let's go ahead and solve for x like we normally would. Go ahead and minus 4 from both sides. We get 15 is equal to 5x. We're going to divide both sides by 5, so 15 divided by 5 is 3. This means that when g of x is equal to 19, when the function is equal to 19, x becomes 3. I'd like you to give this a try. We have h of x is equal to negative 3x minus 2. I'm going to tell you that the function is equal to 6. What is the value for x? Go ahead and pause this and work it out. Push play when you're ready to see the answer. Okay, so if you did this correctly, go ahead and take 6, replace it with h of x, work your algebra, add 12 to both sides, you get 18 is equal to negative 3x, divide both sides by negative 3, x is negative 6. If you got that, rock on. Okay, so on the next page, what we're going to do now is actually start graphing these linear functions, but on top of that, we're going to start doing some comparisons. So when we talk about our comparisons, we're going to use some keywords I'll introduce to you, and then we're going to be very specific as to what the comparison was. So let's go ahead and just first of all talk about who is this. The parent linear function is the most basic function, the most basic line that you will see. And it's so basic that we will have our f of x equal to x. Now, if you notice here, we have a y-intercept of 0 and a slope of 1 over 1. That's how basic this is. So we're going to go and graph that and see what it looks like. Go ahead and make the y-intercept 0. We're going to go up 1 over 1, up 1 over 1. And go ahead and draw a line through that as straight as you can. If you need a straight edge, go ahead and use one. Now this is our apparent linear function right here. This is f of x. So basic. Goes through the origin, goes up 1 over 1, nice positive slope. And what we're going to do here is we're going to manipulate f of x equals x in different ways, and we're going to compare that with this right here, the parent function. So in this example, I'm going to tell you we have the graph g of x is equal to x plus 2. We're going to graph this and compare it to what we have graphed here, the parent function f of x. According to this, we have a y-intercept of 2. We have a slope of 1 over 1. Again, there's a singular x, so we have a 1 over 1 slope. When I graph this, notice we start at 2, and we're going to go up 1 over 1 just like before, and we're starting to see, okay, 1. The slopes are the same, so, okay, they're definitely going to be parallel. Now, if you watch this, again, we have parallel lines. They do have the same exact slope, but what happened is that the difference is we have a different y-intercept of 2. And that different y-intercept of positive 2, it shifted our graph up exactly 2 units. So that's what we're going to say when we compare. When we compare g of x to the parent function f of x, we're going to state this. G of x, where'd it go? What'd it do? It shifted precisely up 2 units. So when we're talking about the comparison for the shifting, we're going to say that it shifted, and where'd it go? It went up. What's the direction, and how many units did it do that? So let's check out this next one. We have m of x equal to x minus 4. So according to this, m of x has a y-intercept of negative 4. We have slope again of 1 over 1. So you're seeing same slopes, and we're going to start down at negative 4 for this one. We're going to go up 1 over 1, up 1 over 1, and put a couple dots there. We're going to go ahead and put a line through this. Now, I'm going to go ahead and label this. I forgot on the other one. It's good to label your lines so you know who is who, because this is f of x, this is our parent function, this is m of x. And we notice if we just take this line, same slope, parallel lines, and we are shifting exactly down 4 units. And that's what we're going to say for a comparison. What happened? M of x shifted. Direction is down 4 units. So we can see that what we did was we just added or subtracted a value to f of x equals x, according to these two. So these are called translation graphs. They shifted the graph up or down. And the translation graphs look like this, same slope of x, or 1x, and either added a b value or subtracted a b value. And if it's add, we went up. If it was subtracted, it went down. All right, so those are the translation graphs. Now, on the next page, let's see what happens when I take our parent function and compare it to n of x is equal to 4x. We have a y-intercept according to this of 0. Our slope according to that is 4 over 1. So we rise 4 over 1. We're going to start at 0 for this to graph n of x. We're going to go up 4 over 1. And I'm going to do that again. I'm going to go backwards this time because I don't have room. I'm going to go down 4, 1, 2, 3, 4, back 1. Let's go ahead and make a straight line right through that. Okay, so this is the graph n of x. And what we notice here is that, well, according to Slope Dude, this n of x is definitely steeper than our parent function f of x. So we're going to say that. We're going to say it's steepened, but how? And that how is exactly the slope. The slope is 4 times bigger. And what we call this is the scale factor. How much bigger did the slope get? And we're going to use this vocabulary. So what happened was that n of x steepened by a, so we're going to go scale factor, we're going to call it SF for short, of exactly the slope of 4. So it got 4 times bigger. And we can all agree now if we have a steepened graph, what happened with f of x is that we just had a slope of m, but the condition is the slope has to be greater than 1 to be steeper than our parent function f of x. All right, so in this one, let's see what happens with the manipulation here. We've got the function a of x, and we have a slope of 1/5, so we're going to go up 1 over 5. Our y-intercept is again 0. So let's see what happens with a of x. We start at 0, we're going to go up 1 over 5, and let's go backwards to fill the whole entire graph, down 1, back 5. And what we notice here is, well, think about slope, dude. He would definitely say this a of x line has flattened out compared to f of x, our parent function. So we're going to say the same thing. Instead of saying steepened, we're going to replace this with flattened, and then we're going to talk about the scale factor. Again, the scale factor flattened by a scale of 1/5. So a of x flattened. Again, we're comparing this to f of x by a scale factor of 1/5. So again, we're being very specific as to what happened. What was the scale factor if we steepened or flattened, and it's right there, it's just slope. So our flattened graphs also have a slope. We have a defined slope, but there's some conditions here. This number is less than 1. So for graphs to flatten, our slope has to be less than 1, but to make it like the flattest you can ever get is a 0 slope. So we have to be between 0 and 1. So basically our slope has to be less than 1 but greater than or equal to 0 for this conditions to be flat. And this last one right here, the reflect, what would that look like? Now I want you to notice right now we have a negative slope of negative 3 over 1, and then we have a y-intercept of 0 still. So when we graph this, I want you to notice there's a negative here, so it's going to be a nice negative slope if we graphed it right. Starting at 0, we're going to go down 3 over 1. I'll go ahead and do that one more time, down 3, and then over 1. So there's a couple things that have happened here. In fact, there's 2 things. This is p of x. We notice right now that it had basically switched slopes. It's a negative slope versus a positive slope. So it did reflect, is what we call it, or it like flipped over. 2, we notice p of x slope is a lot, well, in fact, 3 times bigger than the slope of f of x. So what we're going to say is 2 things because this happened. P of x reflected, and it also steepened by, again specifically, by a scale factor of 3. Now again, this negative is what's the reasoning as to why it reflected. So for all reflect graphs, the parent function just becomes a negative slope, so negative x. And now we know if we were to compare any function to, or any linear function to our parent function f of x equals x, we know exactly what those graphs are going to do if we know what they look like. So again, the translate and the shift graphs are the ones when we add or subtract a b value. The flatten graphs, flattened by a scale factor of whatever the slope is, and that's when the scale factor, the slope is greater than or equal to 0, but less than 1. And then our steepened graphs are the ones that have a slope that is greater than 1, and then our reflect graphs, the reason why we know they reflected is when we have a negative slope. So this ends our topics for today, and good luck on the homework.